Hello everyone and welcome back to tutorial 3 of MIE100, the dynamics course in the University of Toronto. Today's tutorial is going to be about kinetics of particles, particularly force, mass, and acceleration. I'm going to be doing 4 sample questions with you to help you understand the material better. So as usual, if you have any questions or concerns, don't hesitate to shoot me an email or leave a comment in the comment section below. Okay, so let's start with the first question. A small package is deposited by the conveyor belt onto a 30-degree ramp at A with a velocity of 0.8 meters per second. Calculate the distance S on the level surface BC at which the package comes to rest. The coefficient of kinetic friction for the package and supporting surface from A to C is 0.3. Okay. So we know that VA, the velocity at A, is 0.8 meters per second. And the velocity at C is 0 meters per second because that's when it comes to rest. The coefficient of kinetic friction is 0.3, and we want to find out what S is. So we're going to need to use Newton's second law. Newton's second law is, as we all know, force is equal to mass times acceleration. So let's start with a little diagram then. So we know that from A to B, the package is going to look a little bit like this. It's going to be a little bit tilted. So this is going to be our x-axis, our y-axis. And then the mass, the normal force, and the coefficient of friction. Friction force acting in the opposite direction. And this is 30 degrees. So the forces in the y all add up to 0, which means that n is n minus mg cosine 30, because this here is 30 degrees, is equal to 0, which when we calculate it, we get 0.866 mg. Now, the forces in the x direction aren't equal to 0 because the package is moving, so it's equal to mass times acceleration, which gives us mg sine 30 minus coefficient of friction multiplied by n is equal to max. Now when we substitute in the coefficient of friction and our n, we can then cancel out the mass to get AX is equal to 2.36 meters per second squared. Now we're going to use the rectilinear motion equations to solve for the velocity. Now, from what we remember from last tutorial, we know that VB squared is equal to VA squared plus 2A SAB. And when we sub in our values, we can get VB squared is equal to 0.8 squared plus 2, 2.36 multiplied by 2, which means our velocity at B is going to be 3.17 meters per second. Now we want to know how the package is going to look like from B to C. Now from B to C, the package is going to be lying straight. So this is the weight, this is the normal force, and again the coefficient of friction. This time, our y-axis is going to be upright, so is our x-axis. Sum of forces in the y direction is again going to be 0. That means N minus mg is 0. And normal force is just the weight of the package. Sum of forces in the x direction is going to be equal to MA, which is minus 0.3 N is equal to MAX. Sub in the N. The masses are going to cancel out, and we get AX is equal to minus 2.94 meters per second squared. Now, if we use the rectilinear motion equations again, we'll get VC squared is equal to VB squared plus 2 AX S VC. We sub in our values, and we can get our S is finally equal to 1.71 meters. And that's the final answer. Now for question 2, we have a system that's released from rest in the configuration shown at time t is 0. Determine the time t when the block of mass m1 contacts the lower stop of the body of mass m2. Also, determine the corresponding distance s2 traveled by m2. Use the values m1 is 0.5, m2 is 2 kilograms, and the rest of the values are all listed here. So let's write them down again. We have m1 is 0.5, m2 is 2 kilograms, coefficient of static friction 0.1, kinetic friction is 0.08. That's all for mass 1. And then we've got the same coefficients again, but for mass 2. And we've got the distance d is 0.4 meters. Now we want to know the time when m1 is touching the lower stop of m2. We also want to know the distance s2 traveled by m2. Okay. Okay, so let's start off by drawing the diagram for the system. So M2 is lying at an angle like this. the free body diagram is going to look like something like this. So we're going to have the y-axis pointing this way, the x-axis pointing that way. This is the normal force. This is the friction force, the weight of the body. And here we're going to have mass M1. So it's going to have a friction force, it's going to be moving downwards. So the friction force is going to be moving in the other direction. It's going to be here. So it's going to be here like F1. We'll call it F1. And the weight of the mass is going to be pointing this way, M1g cosine theta, where this is theta. So this is the free body diagram for M2. Now, the free body diagram for M1 is going to be a little bit simpler. We're going to have the normal force pointing this way, and F1 is going to be pointing in the opposite direction as in M2, so it's going to be pointing this way. And then the weight acting on it, M1g. All right, so first of all, we want to check if M2 slips. To do that, we're going to first check the maximum force that could be exhibited using the static coefficient. So it's going to be μs2 multiplied by n2, which is m1 plus m2, because m1 is sitting on m2, so you're going to have to count both weights, multiplied by g cosine theta. So when we plug in our values, we have F2 max is 5.76 newtons. Now, then we're going to start calculating. We're going to start calculating the friction needed for M2 to remain still, and if it exceeds the maximum F2 max, then M2 will slip. So we're going to need to know the sum of forces in the y direction, and it's going to be equal to 0 because it's not floating. So on M2, and that's going to be M1 plus M2 g cosine theta minus N2 is equal to 0. And when we plug that in, we can get 0.5 plus 2 multiplied by 9.81 cosine 20 to give us N2 is 23.05 newtons. Now we're going to find the sum of forces in the x direction, and it's also going to be equal to 0 on M2 because we want to find the friction needed to remain still. So we're assuming that it still hasn't moved. It's going to give us M1 plus M2 g sine theta minus F2 is equal to 0. When we plug those in, we get F2 is equal to 8.39 newtons, which is bigger than F2 max. Therefore, there will be relative slippage of M2 occurs. Okay, now we're going to assume that M1 does not slip relative to M2, just for now. And we're going to take the system as a whole to find the sum of forces in the x direction on the entire system. So now that we know that M2 slips, we're going to be using the kinetic coefficient of friction. So mu k M2 plus M1 g cosine theta minus M2 plus M1 g sine theta is equal to M1 plus M2 A. And when we plug in our values, we can get the value for acceleration in the x direction is minus 1.512 meters per second squared. Now we want to check if M1 actually slips or not. We're going to do the same thing we did with M2, and that is we're going to find F1 max using the static coefficient of friction. And we're going to plug in our values. To get F1 max equal to 0.461 newtons. Now, if we find the sum of forces in the x direction on M1, to try to find what the value for F1 is, we can get, so we know the value for acceleration in the x direction, so we can use that to find F1. So when we plug in our values here, we can get F1 is equal to 0.922 newtons. Now this value is also bigger than F1 max, and therefore there is relative slippage on M1 occurs. Okay, now that we know that M1 and M2 slips, now we can start calculating our accelerations on mass 1 and mass 2 individually. So, first of all, we're going to analyze it on mass 1. So, forces in the x direction on M1 are going to be equal to coefficient of kinetic friction multiplied by M1 g cosine theta minus M1 g sine theta is equal to M1, M1A1. And when we plug in our values here, we can get A1 is equal to minus 2.62 meters per second squared. Now we're going to repeat the same thing on M2 to get again, we're adding the masses because M1 sits on top of M2. And let's not forget also the friction force that's acting on M2 from M1. So when we plug our values in, we can get A2 is equal to minus 1.235 meters per second squared. Okay, that's great. Now we have the acceleration on mass 1 and on mass 2. But we want to know the acceleration of mass 1 relative to mass 2. So that's 1 over 2. And as we know, that's going to be equal to acceleration 1 minus acceleration 2. And since we have both, it's going to be easy to calculate. Just going to plug in the values we just found to get minus 1.385 meters per second squared. And now that we have the relative acceleration of 1 with respect to 2, now we can also find the distance that mass 1 travels with respect to mass 2. Now we're going to be using the rectilinear motion equations again to solve this. So this is just the normal rectilinear equation, and we're going to simplify that in a bit. This is going to be 0 because we start at rest, and this is also going to be 0. So this distance over here of the distance traveled of mass 1 relative to mass 2 is basically just distance d. So we're going to plug in d here to get half acceleration 1 with respect to 2 d2 squared. So that's 0.4 is equal to half 1.385 d2 squared. To find the time traveled to get to the stop, which is 0.76 seconds, is the final answer. I'm going to write that again, but in red. This is the time it took from the, basically from this side to this side. Since we have the distance here and the acceleration, we were able to identify the time taken, which is 0.76 seconds. And now we want to find the distance traveled by the whole system, M2. So although M1 traveled 0.4 meters, we don't know how much M2 traveled as well on the whole system. So to get that, we're going to use the same equation again. S2 is equal to S2 naught plus V2 naught T plus half A2 T2 squared. And now that we have the time taken, we can easily calculate S2 because this is all zeros, and it becomes S2 is equal to half 1.235 multiplied by the time taken that we just found, 0.76 squared. And we can finally get S2 is equal to 0.357 meters. This is the second part of the question done. Okay, so now for question 3, it says that a child A is swinging from a swing that is attached to a trolley that is free to move along a fixed rail. Letting L is equal to 2.5 meters if at a given instant the acceleration is 3.7 meters per second squared, theta is 23 degrees, this is theta dot is equal to 0.45 rad per second, and theta double dot is minus 0.2 rad per second squared. Determine the magnitude of acceleration of the child relative to the rail at that instant. Okay, so that's a mouthful. Let's draw a diagram first to help us visualize this better. So we got here a trolley. Let's call it B. It's free to move along a fixed rail. Now, there's a swing attached to it here. There's a child swinging here called A. And he's swinging at theta degrees, and the length of the swing is L. Okay. Now the trolley is moving with an acceleration B, and here the child is going to have a normal motion and a tangential motion. Okay. So, as we know, L is going to be 2.5 meters. The acceleration at B is 3.7 meters per second squared. Theta dot is 0.45 rad per second. Sorry. Theta is 23 degrees. Theta dot is 0.45 rad per second, radians per second. Theta double dot is minus 0.2 radians per second squared. And we want to know the magnitude of acceleration at A. All right. So, before we start, let's talk about normal and tangential coordinates. So we've already talked about this in our previous tutorial. So in the normal direction, the force is equal to MAN, and in the tangential, it's MAT, where AN is rho beta dot squared, and AT is V dot. We've already discussed this before. V is rho beta dot, so when we substitute that in, that could also be equal to V squared over rho, or V multiplied by beta dot. However, here, we don't have a normal and tangential. Here we have a theta and an r. So those are polar coordinates. Those are called polar coordinates. So the forces along the radius is going to be equal to mass times acceleration, the r, and the forces at an angle are going to be ma theta, where ar is going to be equal to r double dot minus r theta dot squared. This is one equation we need to know. And a theta is going to be equal to r theta double dot plus 2 r dot theta dot. This is the second equation we need to know. All right, so let's start solving. So you've got here the acceleration. So if we want to calculate the acceleration at A, here, we're going to need to find the sum of the acceleration theta and acceleration r. So that's going to be r double dot minus r theta dot squared ur plus r theta double dot plus 2 r dot theta dot u theta. Now, r is supposed to be the radius, and the radius here is L. So r is equal to L, and because L is a constant, r dot and r double dot are 0, because when you differentiate a constant, it just gives you 0. So now, let's find the acceleration of A with respect to B. So this is going to cancel out, and this is going to cancel out to give us minus L theta dot squared plus L theta double dot. And when we sub that in with our known values, we can get minus 2.5, 0.45 squared plus 2.5 minus 0.2. And that solves to be minus 0.5 ur minus 0.5 u theta. Okay. Now we want to know the acceleration of B. So if we go back here, we already know that it's 3.7 meters per second squared, but we want to put it in polar coordinates. So it's going to split into cosine and sine. It's going to be AB cosine theta plus AB sine theta. Once we sub in our values, we can get B is equal to 3.41 u theta plus 1.45 UR meters per second squared. Now, we want to know the magnitude of acceleration in the A direction. So far, we only have A with respect to B and the acceleration of B. So we know that the acceleration of A with respect to B is just equal to the acceleration of A minus the acceleration of B. And we want to know this one. So we're going to sub in what we know to get the acceleration of A is going to be equal to 0.94375 in the R direction plus 2.91 in the theta direction, meters per second squared. And to find the magnitude, we're going to square those values and put them under the square root to find the magnitude. And the final answer is going to be 3.06 meters per second squared. And this is the final answer. All right, so for our fourth and last question, we have a 5 kilogram mass placed on a rough inclined surface of theta is equal to 15 degrees to slide with a kinetic friction coefficient of 0.4 and a static coefficient of 0.45. Subjected to a non-constant force, P is equal to 5t in the x direction, where t is measured in seconds. How much time will it take for the mass to reach a speed of 10 meters per second? Okay. So let's write what we know so far. We know the mass is 5 kilograms. The angle is 15 degrees. Static coefficient is 0.45. Kinetic friction coefficient is 0.4. P is 5t newtons. And at V is 10 meters per second, we want to know what T is. Okay, so we're going to start off by drawing the free body diagram. This is the normal force. This is the weight. And this is the P pushing on to the box. Is our y and x coordinates. So we know that the sum of forces in the y direction is going to be 0, which means that minus mg cosine theta plus n is going to be equal to 0, giving us n is equal to 47.38 newtons. So at time is equal to 0, we want to know if this mass starts at rest or, whether it has been moving previously or not. So we're going to test that by first using the static coefficient and making it equal to mg sine theta. So when we plug that in, we have, it'll equal to 8.625, which is bigger than 0. So this means it starts from rest. And the package hasn't started moving yet. Therefore, it has to overcome static friction in the x direction before it can start moving. Now, the sum of forces in the x direction is also going to be 0 because it's at rest. Therefore, 5t1 minus mg sine theta minus static friction coefficient is equal to 0. And when we plug that in, we can get t is equal to 6.8 seconds. Now this time is basically how long it takes before it starts to move. So at 6.8 seconds, that's when the package starts moving. Now we want to analyze it after it starts moving, after T1. After T1, the forces in the x direction are going to be moving, so it's going to be equal to MA. Ft is minus mg sine theta minus the kinetic friction coefficient, mg cosine theta, is equal to MA or mdv over dt. So we're just going to take out dt on the other side, which is going to give us, and we're going to put the m's, we're going to cancel them out. So this is going to be over m minus g sine theta plus mu k cosine theta. Integrate that by t, and integrate that by v. From T1 to T2. So that's going to give us 5t squared over 2m minus gt sine theta plus mu k cosine theta from t T1 to T2, and that's just going to be equal to V. Now, once we plug in the time and expand it out, we're going to get ft2 squared over 2m minus g t2 sine theta plus uk cosine theta plus minus 5t1 squared over 2m plus gt1 sine theta plus uk cosine theta minus b is equal to 0. Now, if we're gonna turn this equation into a quadratic equation, this over here, term over here is going to be a, this term over here is going to be b, and this term over here is going to be c. To be able to solve for t, we're going to have to use this quadratic equation, and we're going to solve it like this. C is going to be equal to minus b, so this term in the middle, plus minus b squared plus 4ac, a is this term, and c is this term, all over 2a. Now, we can use an online calculator, or you can try to solve it on your own, but basically, you're going to have to take the positive t, because t2 cannot be less than t1, meaning that t2 must be bigger than t1. So once you solve that, we can get t2 is equal to 10.8 seconds. And that's the final answer. That was the end of the tutorial. Thank you so much for sticking by and for watching the video. I hope you learned something today. If you have any questions or concerns, again, please shoot me an email at noor.dawidar@mail.tutorano.ca or leave a comment in the comment section below. See you next week.